Hi, I'm João Maltese.
Hi, I'm Filipe Antunes.
Hi, I'm Amélia Ramos.
Hi, I'm Vasco Fernandes.
Hi, I'm Manuel Neves, and we are the Dua Beam team. In this edition of the Student Design Contest, the Antennas and Propagation Society invited us, the students from all over the world, to design a setup capable of showcasing the properties of DOA, direction of arrival, and beamforming. And this latter one is just the capability of changing the angle to which an antenna is pointing without necessarily changing the setup behind it. And the challenge here is that we have to do this in such a way that non-specialists can understand it, and with a budget of only $1,500. So, any idea, guys?
What if we made a setup like a cup game? But instead of a ball underneath one of the 4 cups, we would hide a metal plate for others to find, and through lens they could know if they got it right. To do this, we would need a transmitter antenna array with beamforming capabilities attached to a circuit board that would be connected to 3 potentiometers. By rotating these potentiometers individually, we should be able to see the values of the phase shift changes in an LCD, and in case the difference between them isn't equal, we would see through our software that no beamforming is generated, because the waves are not synchronous. If we were to switch to automatic mode, just by rotating the first potentiometer, we would see all of the phase shifts automatically proportional, such that the user could have more ease of controlling the direction of the beam. Going back to our software, now we should be seeing an arrow pointing in the intended direction. As for the receptors, for the first time, when phase offset is detected, a line will appear that shows where it was detected from. For the second receptor, it goes from red to green as the value of the power increases. Finally, making use of a thread between our antenna and the reflective cup, we achieve a gross estimate of the half-power beam width of our RF link. Now, we need to design the transmitter and the receiver boards necessary for the setup.
Let's first talk about our transmitter board. This may seem complicated at first, but I'll walk you through it. In the beginning right here, we have an oscillator, which will generate a signal that will then be amplified and proceed to 3 power splitters. In 3 of the branches of the power splitters, there will be 3 phase shifters that will shift the phase of each branch in comparison to our reference right here, in the 4th branch, where we can also find another power splitter because the signal of this branch right here will be the reference to one of our receivers. Now let's talk about our first receiver. Right here, we have 4 signals from our antenna array, and also a signal that comes from our transmitter board. This signal will be split in 4 by 3 power splitters. In each of these branches, there will be a mixer. This mixer will compare the signal received and also the signal that was just splitted, and will compare each of them in order to obtain the phase offset. Finally, in our second receiver, we will also have 4 signals coming from an antenna array, where each signal will go through a phase shifter that will shift the phase of the signal depending on the corresponding phase shifter on the transmitter antenna, and then 3 power combiners will combine the signal of each branch, either constructively or deconstructively, depending on the phase shift that was just applied, and then an RF detector will detect the power that corresponds to this signal that was just obtained.
So basically, for our system to work, we needed to design 3 antennas, 1 for each RF port. And that's what we did here. Besides deciding that we want to operate at 5.8 GHz, we were also very concerned with gain and directivity. That's why we chose to design a planar microstrip array, as you can see here, a 4x4, with 4 channels, which will be connected to the transmitter. After a few simulations, we managed to optimize the S-parameter result, but more importantly, the gain that we obtained is very satisfactory for the context that we propose to resolve. Here you can see that clearly we managed to obtain a narrow beam, which will be important for our work, and a maximum gain of 16.5 dBi.
Finally, our transmitter board is assembled. We are ready to test it in the lab. Starting with the tests, we have to first compensate slight phase misadjustments to make sure that when we are sending zero phase shifts, all signals are in phase. First, we are going to test if we can individually control the phase of each transmitted signal, and that's what we see happening here in the blue wave. Now, for the automatic control, we expect to see the wave shifting synchronously to achieve beamforming.
So now that we have optimized this antenna, let's test it to see if it works. In the anechoic chamber, we used a spectrum analyzer to test the antenna and the system. We placed the power supply and the Arduino, and we started with a phase shift of 0 degree, pointing in the direction of an angle of 0 degree. We carefully aligned the transmitter antenna with the reception antenna using a laser, and by manually rotating our system, we managed to obtain the different radiation patterns. We decided to do the measurements in a 5-degree step, and we tested 3 different angles, -30, +20, and 0 degree for the radiation beam. With the spectrum analyzer, we managed to obtain the power received in the reception antenna. Now let's see the results.
After running a few tests, we have obtained some measurements, and in this graphic we are presenting those results, where the orange line represents the simulated results and the blue line represents the measurements we just obtained. In the graphic of the far left, we have the beam pointing straight forward, which means an angle of 0 degrees. In the center, we have the beam pointing to +20 degrees, and on the far right, we have the beam pointing to -30 degrees. As I'm sure you can agree, we are very satisfied with these results.
Even though our goals were specified at the early stages of our project, clearly we could not yet achieve them all. In fact, the variety of topics addressed, the scope of the measurements taken, and the complexity of the subject gave rise to a highly complex project which ultimately led to an incomplete setup. Nevertheless, the team is eager to keep working and finish the proposed setup. And with that in mind, our next steps include the assembly and testing of the receiver circuits and the design of an additional printed circuit board for the user interface. To conclude, even though we could not fulfill the project's goals yet, the entire team sees the results with a positive outlook and faces the next challenges with good perspectives. So, see you in Singapore!